Welcome to Maths with EJD. In this video, I'll be talking about general sum games. Previously, we had talked about zero sum game and non-zero sum games and non-zero sum games. And I have reasons to believe that general sum games are just like non-zero sum games, except that they are kind of a generalization of that, right? So in a in a general sum game, the total payoff, the total payoff to both players can vary. Okay, it's not necessarily constant. Okay, so that's the general idea about general sum games. So straight, can we talk about the general structure of the payoff matrix? Okay, so here you have player one with two strategies A and B, and you have player two with two strategies X and Y. Okay. And generally, you have the payoffs as A1, B1, A2, B2, A3, B3, A4, and B4, like that. So you see that the AIs represents layer one's payoff, and BI represents layer two's payoff, layer two's payoff, like that. And to solve this, right, the step-by-step solution to this, step-by-step solution to this, first of all, you identify the strategies. So you identify the strategies. Okay. Here we see that for A, there are two strategies. I mean, for player one, rather, for player one, you have two strategies, A and B. And for player two, you have two strategies, X and Y. So these are the strategies. Then secondly, you determine the best responses. You determine the best responses, best responses. Okay. I mean, we've done that a couple of times, and we're going to do that again. So, and the idea is whatever one player is playing, what are the best responses for the other player, basically. Then three, we have to check the Nash equilibrium, check for Nash equilibrium, check for Nash equilibrium. Then four, you then solve the game, solve the game, solve the game. Yeah, solve the game. So after solving the game, it's possible that you may get pure strategies Nash equilibrium. If you don't get pure strategy Nash equilibrium, you may consider mixed strategies. Mixed strategies. So if there are no pure strategy Nash equilibria, okay, that's one point. The other point is if there if if players are indifferent, if players are indifferent about, if players are indifferent about their strategies, even with the availability, even with the availability of pure strategy Nash equilibria. So these are the two conditions under which you may go for mixed strategies. Even with the availability of pure strategy, even with the availability of pure strategy, Nash equilibria. Okay. All right. So let's take an example. Let's take an example to drive the point home. So example, imagine as usual, you have player one with strategy A and B, and you have player two with strategy X and Y, and you have their payoffs represented this way: 3-2, then 1-1, 3 for player one, 2 for player two. Then next one, 1-1 for each of them, and 0-0 for each of them in this BX box. And then you have 2-3, 2 for player one, 3 for player two. So you have this kind of thing now. So the next thing you want to do will be to check for the best responses. So let's go for the best responses. So for best responses now, what do you do? For best responses, so you come back here and say, so what if, okay, let's go. For best response, you do it turn by turn. So for player one, you start with player one, for player one, right? So if, for player one, now if player two chooses strategy X, okay, if player two chooses strategy X, that means we are talking about this whole place now. So automatically, player one has two options. Player one has two options, either 3 or 0. And as a rational being, right, player one will choose 3, and that will be his strategy A. So if player two chooses X, we expect player one. So if player two chooses X, okay, player one player one will choose A, okay, because A gives a higher payoff. That's 3, which is bigger than 0, okay. So that is settled. Now, still on player one. So if, okay, now for player one, if player two chooses strategy Y, see, if player two chooses strategy Y, that is what we have here now. So player one would either have a payoff 1 or payoff 2. And being a rational player, we would rather go for option 2. I would rather go for a payoff of 2, such that which will be his strategy B. So if player 2 chooses Y, then player 1 chooses B. Okay. So player 2 chooses X, player 1, okay, player 1 will choose A. If player 2 chooses Y, player 1 will choose B. Player 1 chooses B. Okay. So now we go on to talk about for player for player B. For player B. So what are the options? For player B now? Oh, sorry, for player 2. For player 2. For player 2. All right. So if player 1 chooses, if player 1 chooses A, what does that mean? So if player 1 chooses A, player B has two options, either to go for a payoff of 2 or a payoff of 1. And as a rational being, the player 2 would rather go for a payoff of 2, and that would be strategy X for player 2. So if player 1 chooses A, player 2 chooses X. Okay, player 2 chooses X. All right. Then if player 1, if player 1 chooses B, what does player B choose? So if player 2 chooses, if player 1 chooses B like this, so it means player 2 either has to choose between 0 and 3. And as a rational person, you expect player 2 to choose 3, which is bigger than 0. And that is strategy Y for player 2. So that means that if player 1 chooses B, player 2 chooses Y. Now you see some kind of reciprocity here. So XA, XA, AX, YB, BY. That means these two things are possibly they are possibly Nash equilibria. But I mean, let's do that methodically. Okay. So now that we have chosen their best responses, so let's go for Nash equilibria. So let's talk about Nash or better Nash equilibrium. We don't know how many Nash equilibrium we're going to have. It's possible. I mean, we are used to seeing just one Nash equilibrium, but in this case, we are going to have it a bit different. So let's see. So still using the best response. So you have player 1 with strategies A, B. You have player 2 with strategies X, Y. Okay. And then you have this whole thing. The payoffs 3, 2, 1, 1, 0, 0, 2, 3. So 3, 2, 1, 1, 0, 0, 2, 3. So let's still use the best responses, right? So like we said already, so for player 1, if player 2 chooses X, this is X now. So there are two options, 3 and 0. And player 1 definitely will, being a rational player, will choose 3. So that's that so we can circle that. Then if player for player 1, right? If player 2 chooses strategy X, so that means player 2 has option to choose between 1 and 2. And as a rational player, player 2 want to go for the higher benefits, which is 2. Okay? So that means player 2 will go for this. On the other hand, now, that is for player 1, right? For player 2, for player 2, if player 1 chooses to go for strategy A. That means player 2 can choose between 2 and 1. And since 2 is bigger than 1, player 2 will settle for 2, which is strategy X. Okay. Now, on the other hand, if player for player 2, if player 1 chooses option strategy B, then player 2 can choose between 0 and 3. And 3 being greater than 0 and player 2 being a rational player would rather go for 3, which is going to be that strategy Y. So in that case, we from experience, right? Nash equilibrium, Nash equilibrium exists. Nash equilibrium exists where the where the best responses of the two players, of where the best responses of the players overlap. In this case, we have two. We have two Nash equilibria. We have two Nash equilibria. Okay. The first one is at AX. Okay. Strategy A for player 1, strategy X for player 2. And that is so with the payoff 3, 2. Okay. And the second one is BY. Okay. As you can see, BY, because you see the red and green are overlapping. The best responses are overlapping in those two places. So that's we have two Nash equilibria, AX giving payoff of 3, 2, and BY giving payoff of 2, 3. So we have two Nash equilibria in this case. So it's possible to have more than one Nash equilibrium. Just look at the best responses, circle them, and do it across the players, and wherever they overlap, just are your Nash equilibria. So let's talk about mixed strategies. mixed strategies now. So, mixed strategies. In this game, in this game, mixed strategies are not necessary, since there are pure strategy Nash equilibria, So without introducing probability, we have our Nash equilibria. Okay. However, if the players if the players are indifferent, about their strategies, about their strategies, they can randomize them. That's randomize their strategies so that mixed strategies, can be introduced. So, and that is what I like to do going forward. So in order to introduce mixed strategies, right? So I'm going to do the table again. So here we have player 1 with strategies A, B. Again, player 2 with strategies X, Y. And then we have their payoffs. That is 3, 2, 1, 1, 0, 0, 2, 3. 3, 2, 1, 1, 0, 0, 2, 3. Like this. 3, 2, 1, 1, 0, 0, 2, 3. Okay. Now, one thing we need to understand here is that we have to introduce probabilities since we are doing mixed strategy. So probability of player 1 using strategy A, we can call that P. So probability of player 1 using strategy B, we can call that 1 minus P. Okay. Then probability of player 2 using strategy X, call that Q. And probability of player 2 using strategy Y, call that 1 minus Q. So in that case, we have P attached to this. And then here we have 1 minus P attached to this. Here we have Q attached to this and 1 minus Q attached to this. The reason for introducing mixed strategy here, even when it is not necessary, is because we are assuming that the players are indifferent about their strategies. So that's why we are going this way. So now let's see what happens here. When we introduce mixed strategies. So and it has to be in line of expected payoffs. So in this case, player one's expected payoff, for playing A and B are like this. First of all, if player one plays strategy A, okay, so it means that if player 1 plays strategy A, player 1 playing strategy A means we have 3. So they have 3 here multiplied by this Q, and they have 1 multiplied by 1 minus Q. Okay. So that will be the expected payoff. So it's the payoff times the probability of getting that payoff based on the strategy they play. So that will be 3Q, okay, plus 1 into 1 minus Q. Again, don't forget, player so we are talking about player 1 now. So player 1 to play strategy A, no matter what player 2 plays. So we have 3q and 1 into 1 minus q. So in this case, we have 3q plus 1 minus q, and that is equal to 3q minus q, that's 2q plus 1. Okay, so we have that weighting. Then now, if player 1 plays strategy B, okay, so player 1 playing strategy B, see what that gives us. So now focusing on strategy B, it means that we have 0. So player 1 plays strategy B means, so 0 if player 2 plays strategy X, that with probability Q. So we have 0 times Q, and then we have 2 times 1 minus Q. Okay, so that is 0 0 times Q. All right, 0 is the payoff. The probability of getting the payoff is Q plus 2 times 1 minus Q. That is this. So 0 here and this 2 here. Okay, so that we now have 0 plus 2 minus 2q. So that is simply 2 minus 2q. Okay, so we have that. All right, so we can now say that due to, okay, I guess I can switch this now. Due to indifference, uh, so you see that expected payoff of player 1 for playing strategy A is equal to expected payoff of player 1 for playing strategy B. So that simply means that 2q plus 1 is equal to 2 minus 2q. 2 minus 2q. Then we can collect like terms. So we have 2q plus 2q. That means this comes here and 1 goes. So we have 2 minus 1. So that is 4q equals 1. Okay. So meaning that q is equal to 1 over 4. All right. Of course, this simply implies that 1 minus q will simply be 1 minus 1 over 4, which is 3 over 4. So we have the q's settled. So we have q to be 1 over 4, and we have 1 minus q to be 3 over 4. So this is probability. So q now, this is the probability for playing for B now. So this is the probability for playing strategy X, and this is the probability for playing, I guess that has to be different. So this is the probability for playing strategy X, B's probability, right, for playing strategy X. Okay, so that's probability of player 2 to play strategy X, and this is probability of player 2 to play strategy Y. That's 3 over 4. Okay, so that is settled. Then we now go on. That is for player 1's expected payoff for playing A and B. So let's look at player 2's expected payoff. Okay. Player 2's expected payoff. All right. For playing strategies, X and Y. Okay. So we go and do the same thing. So in this case now, we say if player 2 plays X, we're talking about payoffs now. The expected payoff would be this. If player 2 plays X, okay, if player 2 plays X, we have all this, right? So if player 2 plays X, the expected payoffs are 2 and 0. So 2 with a probability of P and 0 with a probability of 1 minus P, because that will have to be also dependent on what player 1 does. So 2P into 0, 2P times plus 0 minus 1P. All right. So that's 2P. So So for player 2 now, this 2 and this 0. So 2p, 0 minus 1p. So we have, so that will be 2p. So that is 2p plus 0 into 1 minus p. And that is simply 2p plus 0, which is simply 2p. And we have that waiting. Then, if player 2, plays y, then we go for that y again. If player 2 plays y, this is where player 2 plays y. So we have 1 multiplied by p and 3 multiplied by 1 minus p. Okay. So we have 1p plus 2 multiplied by 1 minus p, right? Is that a deal? Yep. So 1 multiplied by p, then 3. It's actually 3, not 2. 3 multiplied by 1 minus p. So this is 3. This is 3. And then we have p plus 3 minus 3p. And that is 3 minus 2p. You know, p minus 3p is 2p. So that's is minus 2p. So again, we can say due to indifference, the expected payoff of player 2 for playing X is the same thing as the expected payoff of player 2 for playing Y. Okay. So in that case now, it means 2p is equal to 3 minus 2p. So 2p is equal to 3 minus 2p. So that means that 2p plus 2p is equal to 3, meaning this comes, right? And then we have 4p equals 3. So that tells us that p is equal to 3 over 4. We have p that way, and that implies that 1 minus p is equal to 1 minus 3 over 4. And that is simply 1 over 4. And just like we had before, that means that, okay, so this is now 3 over 4, 1 over 4. It's as opposed to 1 over 4, 3 over 4 the other time. So here, we now see that probability of player 1, okay, yeah, probability of player 1 playing A is equal to 3, is equal to P, which is equal to 3 over 4. And the probability of player 1 to play strategy B is actually 1 minus P, which is equal to 1 over 4. So we have all these things in place. So so we can now compute the expected payoffs like that. So of course we can pick any of the things we equated. We can pick either of the two since we already equated them. So it means that since the payoffs are there's no difference between the payoffs. So we can just pick anyone, 2q plus 1 for A, or we can pick 2 minus 2q. It's going to give us the same thing. For instance, Q, right? We know Q is 1 over 4, right? Yeah, Q is 1 over 4. So if we do that and substitute here, so 1 over 4. So we have 2 times 1 over 4, that's half plus 1. That is 3 over 2. So if you put the same 1 over 4 here, that will be 2 minus 1 over 2. That should still be 3 over 2. So we can say that therefore, the expected payoff for first player 1 is equal to E of any strategy. It's just E1, right? And you can just pick any of the two things you equated. So this is for player 1. So you can pick 2q plus 1 or 2 minus 2q. It's the same thing. So let's say 2q plus 1, and that is 2 times q. The q we got was 1 over 4. Okay, so this is 1 over 4 plus 1. That is 1 over 2 plus 1 over 2. I mean, plus 1 over 1. That is simply 3 over 2. This is the expected payoff for player one. Then the expected payoff for player two, the expected payoff for player two now. Okay, I don't have to do all the story because we are coming from somewhere. So the expected payoff for player one is 3/2. Then for player two now, for player two, okay, that's either 2p or 3 minus 2p. It's the same. So we equated 2p or 3 minus 2p. So whether it's 2p or 3 minus 2p, no problems because p itself is 3/4. Okay. So that's 2 times 3/4, which is 2 times, that's 3/2. Then same goes if you use 3 minus 2p. So that's 3 minus half. It's still 3 over, no, uh 3/4 now. That is 3 minus 3/2. That's still 3/2, sure. So for player two now, that's simple. The easiest is so E2, and that is 2p, and 2 that's 2 times 3 over 4. That is simply 3/2. So if you use the other expression to you get the same thing. So with this, we come to the end. Oh, or is there any conclusion? Let me see if I need to make any conclusion. Yeah, the all the stories have been made. We have for pure strategies, we see double equilibrium. Probably the first time in this series that we're seeing double equilibrium. And then we didn't need mixed strategies, but we still went for mixed strategies all the same. Okay, still went for mixed strategies all the same. Now you can see the two of them are getting the same payoff. That means that they have found a way to cooperate. So let me just use that as a conclusion. Uh, so conclusion. So the two players, the two of let me put it this way, going by the payoffs, going by the payoffs of the two players, of the two players, they have found a way, to cooperate so as to get the same payoff, something like this. Okay. All right, so this is the end of the general sum games. So you can go over it and see how it all flows. You know, previously I'd used Lagrange multiplier. I see that Lagrange multiplier is totally not necessary if you can master this one, because Lagrange multiplier now includes differentiation and all that, which is not necessary at all. If you can master this way of you know of getting the expected payoffs and equating them, you get the same result as you would get with Lagrange multiplier. And with this, I come to the end of this video. If you have not subscribed to this channel, there's still more coming. I'll be talking about dominated solvable games where we eliminate dominated strategies to arrive at certain results. And of course, I still have like 3 videos in this series for that matter. So you don't want to miss out on anyone. So subscribe to the channel and hit the notification bell so you can always get alerted for each time a new video is released. Then comment, let me know how helpful these videos are. And also let me know if there's a topic I need to teach or a problem I need to solve. I might be able to find time to do that. Then like and share so that more people can have access to this great, great content. Till I come your way again, keep playing the games of life well. Bye.